Thank you all for the interest, for your time, and for being here. I'm very happy to be here. Very happy that I got invited to give this talk to you guys. I was a high school teacher for about 8 years, long ago by now, and I loved it, and I miss it. So it's a nice experience to have a little bit of that feeling once again. One thing, this talk will be about quantum mechanics and why it's a weird theory, actually, and what are the issues in it that make it difficult to make sense of that theory, even though the theory works. And that's something that we philosophers of physics do. That's not one of the subjects to which philosophers of physics pay attention. We learn physics and then think about philosophical questions, conceptual problems that the theories may have, and study about that, and write about that, and argue about that, and fight about that. And I work in the Catholic University here, and that's pretty much everything about me. Do you have any further questions? One thing, normally when I give talks for academic audiences and stuff like that, the way to proceed is that you give your talk and then there's a questions and answers section. But if you have any doubts, take it more like a class, like as if we're giving just a regular class here. Okay, so if you have any questions, something that is not clear enough, please don't hesitate to interrupt. Okay. And actually, it's nice when those questions come up. Okay. In order to understand why quantum mechanics is weird and why do we need to interpret it and try to work with it to make sense of it, it's always useful to compare it with the rest of physics. Because the rest of physics is not weird in the same sense. The rest of physics we can make sense of. Of course, there are lots of things to say about the rest of physics too, but quantum mechanics is special in that sense. Again, the rest of physics is not weird in the way that quantum mechanics is weird. So a useful way to understand why it's weird, so let's take a look why the rest of physics is not weird. This is the way that most physical theories work. Okay, they start by defining a mathematical object that comes from some mathematical formalism. It can be a function, it can be a vector, it can be whatever. But we use that mathematical object to represent the state of a physical system. A physical system is just an object, okay? Something that moves, has properties which are that makes it interesting for physics. Just a physical object, okay? But we use the word system to do that. So there are physical systems, and they are in a certain state, okay? For example, they will have certain values for certain properties. They will have a certain amount of energy. They will have a certain amount of momentum. They will have a certain amount of mass and stuff like that. Okay. So we use mathematical objects in order to represent those properties. So in all physical theories, there is some mathematical object that plays this takes charge of representing the state of the system. The state of the system, you can think of it as a sort of photograph of the physical system at a certain instant. It gives you the information of what's the state of that thing in the world at that moment. For example, in Hamiltonian mechanics, which is an alternative formulation of Newton's theory, that is no more than that, the mathematical object that we use to represent the state of a particle, of a classical particle, is this order pair. Okay, these two coordinates in a certain space. This Q here represents the position of the particle, and this P here represents the momentum of the particle. So if we say where a particle is and what is its momentum, then we have that picture I was talking about. Okay, but that picture holds for a certain instant in time, and this is what we call a point in phase space. That's the space in which Hamiltonian mechanics is defined. Don't worry about it. Sometimes these facts sound a bit scary, but Hamiltonian mechanics is just the physics that you learn, guys, formulated in a fancier formalism. So, as I said, position Q and momentum represent the physical state of a system in Hamiltonian mechanics. But that's the picture at an instant. Okay, but apart from the object representing the state of the system, we have physical properties. We have properties for that system. Okay, just like human beings have a certain height, a certain weight, and so on. Physical systems have a certain amount of energy, have a certain, and so on. Okay, and we also use mathematical objects to represent properties. And in classical mechanics, there are always functions defined over the representative of the state of the system. We simply take this point in phase space, and we define a function which will be a certain mathematical operation that we perform on this, and then we will get a result. This will be equal something, most of the times a number. So we say that the function f represents a certain property, and when we apply the function that represents that property on the state of the object, we get the value for that property that the system has. It follows the idea, you know, that a person is a physical system and height is a property. Then we perform a certain action on the object, which is a person, and then we get the value of the height. Okay, it's the same thing. Okay, a function is just these functions give us the properties of the system. For example, kinetic energy. Okay, the energy that is associated to motion. Everything that moves and has mass has kinetic energy. Okay, how is it defined? Look at that. It's mass times the square root of the velocity divided by 2. But m times v is momentum. So if you take a look, then this function here, kinetic energy, is a function of momentum. We take momentum, which is representative of our state, apply this mathematical operation, we solve it, and then we get the value of the energy that the object has. Okay, the kinetic energy that the object has. And yeah, as I said, using these functions, these functions, we can obtain the value of the corresponding property, as I said, that the system possesses. We solve the mathematical operation, and we get the value for the property. That's all. And the third piece, this is very important. We now have a picture, right? And we have a certain recipe. So given that picture, we can know what are the values of the properties that the things represented in the picture have. Okay, but that's just a picture. We are still at an instant in time. We need to press play, right? And then we get a movie. We do that with, and that's the concept of time evolution in physics. As I said, the state of a system gives us a photograph, but we now want to see how the picture goes. And there's, again, yet another mathematical object in the theory that allows us to have that evolution in time. And our equations that always have this form. Okay? They're always derivatives with respect to time. The only thing that if you know calculus, you know what I mean, but if you don't, that only means that we are saying how this quantity changes over time. That's all. Okay. So, and then if we have those equations, then we have the dynamics of the theory. We have we can tell what's the physical history of a certain physical object. And again, in Hamiltonian mechanics, we have these two equations. If you see, this equation tells us how position changes over time, which is pretty much velocity. And we have here how momentum changes over time. So we know how position and momentum change over time. We know how the system changes over time. Okay. But in order to solve this equation, we need this H here, which means the Hamiltonian. The Hamiltonian is simply the total energy of the system, which is the kinetic energy plus the potential energy. It will have an expression similar to this. This is only kinetic energy. Potential energy has another respective function, but with kinetic energy plus potential energy, we have the total energy, and then we can solve the Hamiltonian equations, and with that we have the picture. We can press play, and then we will see how physical objects behave over time. Okay? All physical theories work in the same way. They have different mathematical objects and stuff like that, but the general picture is the same in all the rest of physics. But as we will see, things will get weird in quantum mechanics. One thing, these two equations are actually equivalent to Newton's second law, which is in the Newtonian formulation actually plays the role of this play button. And one important thing that, because it will be useful later, H, the Hamiltonian, codifies the total energy of the system. And what the total energy codifies is the way that that system interacts with the rest of physical objects around it. Okay. The Hamiltonian tells us in what kinds of physical transactions that objects get involved. And since we know that, then we can know how the object evolves. Okay. Now, everything I have said can be cashed out in two conclusions. Okay? First of all, the predictions for the outcomes in experiments, in laboratories or whatever, the predictions I can get from here, we call them deterministic. That means that if I know the state of the system, I have my time evolution equation, the Hamiltonian equations, for example, and I have everything else that I need to describe. I know everything exactly, I know precisely, univocally, everything that's going to happen to that object until the end of time, actually. And actually I can know also what happened to that object since the beginning of time. Okay. Classical mechanics is a deterministic theory. Okay? And all theories in physics, apart from statistical mechanics, but explain why it's not a problem. Most of classical physics is just deterministic. Okay? So if we know the certain state of a system at some time, I can know everything else about it over time. And second, there are anyway in classical physics some theories that use probability instead of determinism. Probability means that, okay, I cannot tell you exactly what's going to happen, but these are the possible options, and we can assign probabilities to this result or this result. There are some theories in classical physics that work like that. Statistical mechanics, climate science, stuff like that. But we get probabilistic predictions when the picture we have, when the description of the state is fuzzy, so to speak. That means that we get probabilities when our description of the state of the system is incomplete. There are things about the system that we just don't know. And since we don't know exactly what's going to happen, but we know more or less what's going to happen, and we can assign probabilities to it. So in the framework of classical physics, when we have probabilities, that means that there's something we don't know about the system. Okay. That's why the weather cannot predict with certainty. For example, if we could describe the state of each and every molecule that conforms a tornado, then we could say exactly how that tornado is going to behave in the future. But of course, we don't know that. I imagine the amount of molecules that constitute a tornado or a storm or whatever. We don't know that. We have a sort of average description of the whole system. And since we only have that and not the full description of the system, that's why our predictions will be probabilistic and not deterministic. And second of all, and another thing, remember the functions here that represent properties, they behave well, mathematically speaking. That means that given a certain physical object, I can know what is the value for all the properties of that system. Okay, there are no how you say elements properties that I don't know about, okay, or that get indeterminate or anything like that. All the properties of a quantum system are well defined in classical physics. But now, quantum mechanics. Quantum mechanics has a very fascinating history from 1899, when Max Planck publishes the first paper about it, until 1927, when John von Neumann presents this formalism in a paper, and then in 1932 in a very important book. And the people who participated in the formulation of the theories: Planck, Einstein, as usual, Niels Bohr, Arnold Sommerfeld, Werner Heisenberg, Niels Bohr, Wolfgang Pauli. Those were very important in the formulation of the paper. But now, okay, we have quantum systems again. We have quantum objects, but now we won't represent them with this ordered pair of position and momentum. We will represent it with something else, with a vector in Hilbert space. Okay, this ket is called. That parenthesis like this is called the ket, and that indicates that what we have here is a vector. the vectors that you all know that have certain magnitude and certain direction. Right. And the m psi here is called the wave function. I will tell you now where it comes from. Okay. But the thing is that we represent the states of system not with points in phase space, with this q and p. We represent states by vectors in Hilbert space. Okay. Now, how do we represent properties? We use another, again, we don't use the usual functions that we use in classical physics. We use a different kind of mathematical objects, which are called self-adjoint operators, which are mathematical objects that are defined inside Hilbert space too. Okay. So we take one of these operators, we make it to operate over our quantum system, and then I know what's the value of this system for that property. The same idea, but with different mathematical objects. Okay. And time evolution is not given now by Hamiltonian equations or by the Newton's second law, but by the Schrödinger equation. Okay, and as you can see here, is a derivative over time. So this means that this equation tells us how this vector here evolves as time goes by, okay, or either forwards or backwards. And this again here is again the Hamiltonian, but now it's not a function; it's an operator. That's why it has this little hat here. That's the difference. But again, the Hamiltonian is important. And we have these two weird guys here. That this already indicates us that there's something different now. We have first the imaginary number. That's weird. That we have complex numbers participating in physical theory. And we also have the Planck reduced constant, okay, which is a constant that doesn't appear in the surface. But now, we hope in classical physics, a system in any state, whatever state, always has a determinate value for any property. Okay. There are no properties that, okay, we don't know what's the value of the property, or we cannot say that the property has a value. They always have. But with, I'll say it briefly in math terms, but then I will explain conceptually. Self-adjoint operators, the representative of properties in quantum mechanics, are not like the functions in classical mechanics. Self-adjoint operators behave in a strange way, mathematically speaking. In particular, this is true for some self-adjoint operators. If we multiply the operator Q by the operator P, we don't get the same result than as multiplying P times Q. For some operators, the multiplication is not commutative. Okay, that happens. That's a property of this mathematical framework. Okay, that's something that doesn't happen with functions, but happens with self-adjoint operators. And but this has a consequence, and this is what's really important here. If you don't understand this, never mind. But this weird thing here has a consequence for the physical representation of system. We have that if a quantum system has a determinate value for property P here, okay, let's assume that we ask, okay, and P is this can be the momentum operator, okay, we want to ask what's the momentum of an electron, whatever, okay. Then we take this operator, do the calculation on the state vector, and then we get the value for the momentum of that particle. But if we have that, since the representation, the object that represents momentum here does not commute with the object that represents the position, that means that if I have a determinate value for momentum, then I cannot have a determinate value for position. And that's not because I cannot know it. The formalism doesn't allow me to have that. And the other way around. If I know exactly where the particle is, if I know its position precisely, then since the position operator does not commute with the momentum operator, then I don't know what's the momentum. Or what we have to say is that for the if the system has a value for position, then it doesn't have a determinate value for momentum, and the other way around. And there are lots of operators that for which this occurs. Okay, and this is, for example, maybe you have heard about it, Heisenberg's famous uncertainty principle, which expresses this. For example, if I want to know position and momentum at the same time, so I want that my delta P
saying that we know it's
guys, I'm gonna be a high school teacher again. Ask your questions loud so I don't get.
Oh,
If you have comments.
So,
Yeah.
the second point about QP not being equal to PQ,
Yeah.
does that have anything to do with why is it so hard to find an electron?
Partly, in some cases, of course, because if you I mean, finding the position of an electron is always different, of course, technically, of course, right. But if you are doing an experiment that you are interested in momentum, then of course, you know that you will never know where the particle is, or more precise than that, actually, and this is the problem. It's not that you don't know where it is. The point is that the question where it is, where is it, is meaningless, because if it has a certain value for momentum, then it just doesn't have a position. It's really weird. Okay? And the other way around, if our electron has a determinate position, then it doesn't have a determinate momentum. It's not that I'm not able to find it. At least in a standard interpretation of the theory. There are other interpretations, and we'll talk about it by the end of the talk. It's different, but that's the problem. Okay, it's more than I cannot know where it is. Okay, if I know the momentum. The point is that if the system has a well-defined momentum, a numerically defined momentum, then it just doesn't have a position, which is really weird. What does it mean that a particle, like an electron, doesn't really have a position? Which is, as I will show you, it is a superposition of position, which is really weird.
Yeah.
All of this leads to the, probably you have heard of Schrödinger's cat.
Yes.
Yeah.
I'll talk about it. But then again, okay, remember, if I have well-defined momentum, then there is no position. Okay? There's no well-defined position. But then, if I have a property, okay, which is like position in this case, I don't have a determinate value for that position. Okay. If I want to make predictions for our state regarding that property for which there is no determinate value, okay, then all my predictions will be probabilistic. Okay, and there's no way out of it. Again, if I have well-determined momentum, then there's no determinate position. But if I want to know something about position in measurement, the only thing I can do is predict probabilities that I will find the electron here, probabilities that I will find the electron here, and so on. Okay, that's how probability enters in quantum mechanics. And yeah, and this is a sort of essential feature of the mathematical formalism. It's not a limitations about what we can calculate, about what we can, we say, write down and look for in the lab. It's something that is written in the formalism, in the theory itself. Okay? It's not something that I can reduce probabilities to or something else or whatever. It's built there. For example, there are two properties. There's a property called spin. Okay, like the self-rotation of a particle. That we can measure it either in the x direction or in the y direction. Okay, that's a quantum property. And this property spin has only two possible values. Okay, every quantum object has a spin, but the spin value can take only two values, +1 and -1. And when it's +1, we normally say that that's spin up, and when it's -1, we normally say that that's spin down. Okay, spin in a certain direction for a system only has two possible values, up or down. Okay. And these two operators don't commute. Okay, for those two operators, this is true. And then, if we have that our system has a definite value, say up for spin in the x direction, it just doesn't have a determinate value for spin in the y direction, and the other way around. Okay. So if we know that our electron has spin up in the x direction, we know that it doesn't have a determinate value for spin in the y direction, and for that property we can only do probabilistic predictions. And this is important. Okay. The mathematical properties of the formalism means that if I have a system and I know that it does have a determinate value for a certain property, it's guaranteed that there will be other properties for which it doesn't have a determinate value. Okay? That indeterminacy of property values will happen, yes or yes. There's no way out of it. We can only have determinate values for a certain set of properties, but for the rest of the properties, the system won't have a determinate property. And if we think that position won't have a determinate value, to say that, again, the question of where's the electron is not really well defined. It is really weird. I think I hear that, and yeah, and this is also the last thing about quantum mechanics that I will explain, and then I'll tell you a bit about how people deal with this, or what are the options to get out of this state of confusion. Okay, let's assume that we have a quantum state, okay, which we know that is spin up in the x direction. Okay? I know I have an electron, and I know that it has a spin up value for in the x direction. We start out from that assumption. And then we make an experiment. We send our electron in the spin up in the x direction into a device in the laboratory that measures spin in the x direction. Okay? Then the point is this: the detector also has a state, that the initial state just before the experiment, and we put an R here because that's the rate state. Okay. And then, since we have only two possible values for spin, up or down, then of course our device will have, I don't know, two lights, a green light and a red light, that will tell you when the experiment is done. So the final state of the apparatus can be one of these two. The screen showing me spin up, and the screen of the apparatus showing me spin down. Okay. So if this is a measurement, then if I feed the device with an electron in a state of spin up, and it interacts with the device which is in the ready state, then the outcome I will have is that, of course, the electron's still on the spin up state, but now the device tells me that. Okay? And the same happens if I feed the device with a spin down electron. This will be the interaction in the experiment, and the evolution will be this. I will get spin down, and the detector will tell me that it's spin down. And this arrow here represents the Schrödinger equation. Okay, it is the Schrödinger equations that I go from this state to this state, and that I go from this state to this state, and that's fine. Okay. But what happens when I get superposition states? These are the states which are weird. Remember, I know that my electron has a spin up value for an up value for spin in the x direction. But remember, spin x does not commute with spin y. So for spin y, it won't have a determinate value. And this is the representation. This is just the same here, but now I'm talking about y spin in the y direction. And here I cannot say that the electron is either up or down. What I have is this is called a superposition. It's a linear combination. This is a vector made out of two vectors. This is just a linear combination of a bit of spin up and a bit of spin down, but neither, and not both at the same time, because that's not possible. So what the hell is this? We're not really sure. What does it mean when I represent a state with a superposition? That's weird to think about. Furthermore, and now we have a problem. Let's assume that I want to measure spin y, okay? But on this electron that I know is spin up, but in the x direction. So I feed this electron, which doesn't have a determinate value for spin in the y direction. I make it interact with the measuring device, and what the Schrödinger equation tells me is that what I get after the measurement interaction is again a superposition. So what the theory tells me is actually that because of this, the measuring device will also go into a state of superposition. This means, check it out, that the state of the device is also a superposition of green light saying up and red light saying down. But that doesn't happen. We never find measuring device which are in something like this. But what we find is either this or this. Half the times when we use a particle in this state, half the time we get spin plus, half the time we get spin down. Okay? But there's something weird here because this is not what the theory tells us actually. Because let me. No, I don't have it here. Yeah, but so what we will have is something like this. You know, I will interact with this. So the point is that what I get in lab results is that this interaction between my electron and the device, half the time I get this, and half the time I get this. Okay. But the point is now this arrow doesn't represent the Schrodinger equation, and here we have a problem because I know that this interaction results in this result, but that's not what the Schrodinger equation tells me, and the Schrodinger equation should hold in all cases. So the Schrodinger equation doesn't give me what I find in the lab. But what the hell is going on here? Yeah, this is called the measurement problem, and it's one of the most important problems in quantum mechanics. And that's what the Schrodinger cat experiment illustrates, and that's a paper by Schrodinger from 1927. Imagine that you have an electron that doesn't have a determinate value for spin up in a certain direction. Okay, you make it interact with a certain device such that if the electron were in spin up, a certain mechanism is activated which breaks a bottle with cyanide in it, with this super powerful poison. Okay, and if the spin of the electron of the particle were down, the hammer doesn't fall, and so the bottle doesn't break, and the cyanide doesn't come out. Okay, but if I feed an electron which is a superposition, which is neither spin up, neither spin down, but a superposition of both, the resulting state will be that the bottle will also be superposed between a broken state and an unbroken state. Assume that we get a little cat, you know, and we put it in a box, and then I run quantum mechanics. Then again, if I use this superposed electron, then the result is that my final result, what the Schrodinger equation tells me that what I should get, is a cat that is in a superposition of being alive and being dead. Because if the bottle breaks, the cat dies because of the cyanide. If it doesn't, it won't die. So Schrodinger says that, and be careful about that. Lots of people understand that Schrodinger wrote that papers to show us how strange quantum mechanics is, but that was not his intention. His intention was saying that this is a problem. This cannot be. We have to solve this somehow. And that's the work of other physicists, and that have proposed different interpretations of quantum mechanics. And the goal of these interpretations of quantum mechanics is try to solve the measurement problem that I just described, and try to give us a clearer picture out of reality and from the theory. And there are many ways to do it. Actually, there's a long list of different interpretations. Those interpretations, this is what they are. Okay. And yeah, there are different types of approaches here. Okay. One is called the hidden variables approach. What do these people say? They say that the state vector is not enough. That's not the complete representation of the state of the system. Okay. That we are missing something. And they say if we add this something that we are missing, then we recover determinate values for all properties, and we recover determinism. Okay. But what is that we are missing? Okay. Well, not easy to know. But there is one particular theory by David Bohm from that year that does exactly that. But it's very appealing. It's really cute. I really like it. I've worked on it. But despite its appeal, it has also problems. Also, really weird things happen in this theory too. I won't go into that. But yeah, we have an alternative. This is the more conservative approach. This is something like trying to go back to the classical picture of the world. But not quite, because it's also has weird stuff. This one you will find it especially weird, I think. I hope. The many worlds interpretation. remember again the cat, okay? And they say, okay, there's no measurement problem, but what happens is that when I make the measurement, when I measure the spin of the electron that was in a superposition, what happens is that both results, the dead cat and the live cat, living cat, turn out, both results happen. The point is that they happen in different universes, in different worlds. That means that by performing an act of measurement, when I measure a superposition, a state in a superposition, what I'm doing is to split the world in different branches. Along one branch, the cat will be dead, and in the other branch, the cat will be alive. And there's no interaction between the branches of the world, which is really weird. This is a very elegant maneuver because it doesn't force us to do any new mathematics. It doesn't force us to change the theory. It holds it just like as it is, and that's the attractive of it. It sounds really weird, but for example, I don't know, the School of Philosophers Physics in the University of Oxford, for example, they like it. I don't understand why. I don't like it at all. But that's something that's more or less possible. And the last one that I will talk about is the family of spontaneous collapse interpretation. Here what's going on is that they say that the Schrödinger equation is not the last word, we have to fix it. They add something to the Schrödinger equation, and that they add does this work of allowing me to go from a superposition to a determinate state. But that happens random, and it doesn't have to do with measurements, it just happens in nature. And they add it and they manage to do it. But also has some other shortcomings, and there are people working on it, some other people don't like it. And these are the three main families of interpretations, and there are people supporting each one of them. I like Bohm's theory, but I'm not a supporter. I studied it. And some people, many people are agnostic also. We study all the interpretations, we try to understand them, we try to work with them and so on, but we're not forced to choose. We can keep on working. That's more or less what I do. And that's pretty much it. Actually, yeah. The current situation is that there are pros and cons in all these interpretations. Some physicists, some philosophers endorse one of them, they defend them, and they argue, they fight about it, and so on. But an interesting thing is that working physicists, remember, I'm a philosopher of physics, I'm not a physicist. Practicing physicists, they pretty much don't care about these things. And the reason is because to do what they are supposed to do, to solve the problems that they are set to resolve, they don't need to solve these problems first. This doesn't have an impact on the application of the theory. And that's why physicists usually don't pay attention to these things. And during some time they were kind of, I say, hostile toward philosophical analysis like the one I did here. That's changing because of many reasons. But for philosophers of physics, this kind of discussion is, of course, central, and this is what we do. We spend a lot of time studying this thing, writing stuff. Because, well, why is it so important? Because what interpretation is the one I choose, on that depends what is the description and explanation of the quantum world that I adopt. I don't have the time here, but all these three alternatives, we could study them. Okay, what they say about the world is this, and then I take the other interpretation, it says something very different. And I take the other interpretation, it says very different. But they all make the right predictions, so we can discard them experimentally. So it's a sort of aesthetic, epistemic preference, like that. And it's that's a lot of fun actually to try to understand how any of these interpretations, what they tell us that the quantum world is like. But as the current situation, in the state of the current situation, we cannot make a choice. Okay. That's more or less the general picture. Thank you. Okay. Do you have questions?
All right.
It doesn't have to be about this. I know that
it is a good idea that there are like different ideas and that like they all differ. Like, does that lead us to a better answer or to a worse answer?
that's a very good
Bad
question actually.
For the actuality of the future.
Yeah, exactly. That's part of it. It's a controversy, actually. There are some people saying that, for example, there are some people who are very fanatic about some of these interpretations, and they get in really rough and sometimes even arguments. I've seen some of those things like that. And those people normally think that, okay, I can convince everybody else that this is the way to go, and this is the way to go because this is the correct way. Some people that science should work in that way. Some other people, among them myself, think that a pluralist stance is better. That, of course, this type of pluralism indicates that we have a problem. We don't really know what the theory says about the world, and we cannot choose one of the interpretations and so on. But there are also other challenges in physics. For example, the quest for a theory of quantum gravity, which is supposed to be the next step in physics. We don't have anything like that, but this is what we want to have. Okay. And of course, the development of quantum theory will be important. And if some people want a theory of quantum gravity and they like one interpretation, they will do some things. Other people that like a different interpretation and they want to do quantum gravity, they will follow a different strategy. And those that think that a pluralist attitude is better is because they say, okay, let's explore all the possible alternatives. And there are other people who say, no, we should go unified and so on. But that's a controversy, actually. There are current discussions about that. I would like to write about pluralism.
Do you think like it will never be a definite world, theoretically, like in quantum mechanics, it'll never be a
Like one answer.
like a book of what it is and what is not. It'll never be like that, right?
It depends. We just don't know because we know what are the scientific problems that we want to solve. We know what more or less should how the theories that we want should look like, but we never know how the development of physics is going to be. It's always, many times it's very surprising, and that's why we call some people especially genius. What Einstein did, I don't know, by 10 years before the work of Einstein, nobody would have ever imagined that somebody would come up with a theory like relativity, and that we would be accepting that. That was, Einstein had a special mind, and he solved the problems in a particular way, which nobody expected. And sometimes the change is more, not so obvious. Now we are more in a boring moment of physics. Nothing exciting has happened for a while.
You may change
Yeah, if you want to study physics and maybe you can come up with a quantum gravity theory. That's what we want, but we never know. We know we know more or less. Okay, this is what we want. It should look more or less like this, but that still leaves a very wide space of possibilities, and we don't know how it's done.
Right.
Did you tell them that you want to study physics?
No.
You should.
Just say it.
Yeah. I want to study physics.
Cool.
I don't know exactly what, but one area I want to, but I want to.
Yeah, but that's something you don't decide at the beginning. You just enter
exactly.
a physics program, and then you get to learn that it's experimental physics, theoretical physics.
Yeah.
And so on.
Exactly.
Yeah,
That's
go for
right.
it. Go for it.
Yep.
How old were you when you knew that you wanted to study physics?
Oh, weird. No, my story's kind of weird. I'm sorry. When I was in high school, and I was very good at math, but I was also very good at humanities. I like to read and stuff like that. And when I had in the high school, I studied when going to tercero medio, to the third year in the second cycle. You have to choose sort of a specialization between the mathematical branch, the humanities branch, and the biology branch. And it was terrible for me to make the choice between the humanities branch and the mathematical. And I went for humanities, and not for math. I mean, I had math, but I had less math than others. Okay. And my first degree in the uni was actually literature, which I finished. But studying literature, I had some philosophy courses which I liked, and say, okay, I like this even better than literature. I I studied literature, but I partied a lot actually. First 2-3 years were kind of good. And but then I found philosophy and I stopped partying a bit.
Okay.
and I noticed that okay, I like this. And then, but in philosophy you study Plato, Aristotle, and all that stuff, which is great. But then at some moment I discovered that I discovered Kant first, and Kant thought a lot about scientific knowledge, and that's very interesting. And I wrote my undergraduate thesis about that. And then I discovered that there is this thing called philosophy of science. Okay, that's cool. I started to go back to it, and I did a master's program here in Santiago, in University of Santiago, on philosophy of science, which was general. It was not really about physics. But then I decided, okay, I want to make a PhD because I want to do an academic career. And then I decided to go to the Netherlands, and I didn't know much about it at the moment. I chose that particular university, the University of Utrecht, because they have a dedicated program for history and philosophy of science. And I know, okay, this is gonna be nice. And then when I arrived there, I noticed that many of the professors were philosophers of physics and people with a serious training in physics, which I didn't have at that time. And I said, well, okay. But then kind of the environment sort of took me in the direction of going back to study things like physics, and say, okay, what the hell, I'll go for it. I had to study a lot of math by myself and a lot of physics by myself. I had the time, fortunately, so and I said, okay, I'm back to segundo medio. And yeah, I'm happy that it happened that way actually. But yeah, I don't have a formal training in physics, so that I'm in physics and in math. I'm pretty much self-taught, and I still have to continue. There's more math I would like to know if they give me the time in the uni.
Pablo, did you study Gaston Bachelard?
I know about him.